Hi, welcome to another lesson at EDU Solutions Institute. Now, on today's lesson, we are continuing on the IB Physics syllabus with the HL topic of relativity. Now, on last week's lesson, we looked at Maxwell's equation or Maxwell's view in terms of relativity, as well as we look at the Lorentz factor and its effect on time and distance based on reference frames. So stay tuned this week as we continue on relativity, looking at time dilation and length contraction. Now, time dilation. As the name suggests, time dilation means that time is dilating. Dilating means time is changing, more on the end of getting smaller. Now, what effect does motion have on time? Does it have any effect? Or does motion just makes time constant if it was stationary or if it was moving? Now, according to Galileo and Newton, those aspects made that time is an absolute in the universe, which means it doesn't depend on motion. But according to Einstein, he says that's not the case, and time will be measured at a different rate in different reference frames. So let's explore more on that aspect of time being different in different reference frames. Now imagine this situation here. We have a simple diagram here of a clock that generates a photon of light and a mirror that reflects that photon back to the detector. So examine the picture on the right side, we see that the clock produces the light, it goes to the mirror, and the mirror reflects that specific light. Now, if we look at the second observation, this is when there's relative motion, and that's what we will see when it goes towards the mirror and then it reflects away from the mirror, right? So the clock is turned on and examined from two reference frames, one moving with the clock and the other is stationary viewing the clock from afar. So therefore, the one that goes with the clock goes in a vertical motion. The one that is observing from a distance will see it going at an angle, then reflecting back from an angle. So the path of light has been shown by the observer will be different, as we can see, right? So therefore, if we shine light onto a mirror and the mirror reflects that light, if you're going with the light, then that means you will see it just as going in and out. While if you're observing that event from a different reference frame, then you're going to see going at an angle and being reflected at an angle. Now, the observer moving with the clock will see the event taking much shorter than the stationary observer. And that's what we can see here. The distance that moves between the stationary observer and the moving observer, there is a big difference. So if we examine for the person moving with the light, we see that their distance would be going to the mirror, coming back, right? So therefore, in this case, it would just be 2D as their distance going and coming back, and the speed would be c, the speed of light. So hence we get a time of 2D over c. Now let's look for the stationary observer. Now if you're looking at the event, the person will see light moving in a distance, capital D instead of common D. He's going at an angle. So therefore, that capital D is much greater than the small d, right? So therefore, In this case, it will be 2 capital D, right? So it's going towards the mirror, reflecting away over speed of light c. And that would be the time that the stationary observer will observe for this event. Now, because d is much greater than common d, then we say that the time that the stationary observer will observe this event would be much greater than the time that the person moving with the event would observe because of this difference in the time frame observing. So therefore, that means that we have some time dilation. There is some difference between the time of the same event, but in two different reference frames. So therefore, in relativity, we now have to incorporate an equation to see that the time in all reference frames are not the same. And hence, we use the Lorentz factor to actually include in our equation to tell us that time is changing based on the reference frame that you're observing the event from. And that's how we will have our equation, right? Which tells us that the t represents the non-moving reference frame, the t prime would represent the moving reference frame, the v is the speed of the moving reference frame, and c we know is the speed of light. All right, so if we take this in an example, we see that two clocks are synchronized before one is placed at a high-speed spacecraft. The spacecraft travels 2 hours ship time at 0.90 c, which is 0.90 times the speed of light. How much time will it have elapsed on the stationary clock? All right, so one of the clock is placed on the spacecraft and sent off into space, while the other clock is stationary on Earth. All right, so therefore, what we're finding is a t, because t represents the time on a stationary reference frame. All right, so therefore, t prime would be the 2 hours. All right, we put in the v, which is 0.9 of c, and we're squaring that, and then we divide by c squared. All right, so therefore, we end up with an answer of 4.36 hours. And what this means is that first, the clock that is observing the event on Earth stationary is observing it over twice the time that the clock that is traveling with the spacecraft is observing or recording the time for that event. All right, same example in this case as well. Now, let's look at the term of length contraction, right? So there's another way to look at time dilation. If we examine this spacecraft here, it is traveling a distance of 5 light years to reach to a specific galaxy. Right? The ship takes this trip in 1.76 years. Now, Earth time says that the trip takes 5 years because it's 5 light years. But for the persons on the ship, they're saying it took 1.76 years. All right, so that's also time dilation being experienced. Now, if we look at length contraction, all right, length contraction has to do with the event reference frame and how do you see distance changing or length changing, right? Now, if we take, for example, we throw a ball from one person to the next in front of us in a projectile manner, right? If we have an observer moving with the ball in that same projectile motion, then the distance move would be in the projectile like that. Now, right, it will move in a more of a straight line. But for a person observing the event from the front view of that event, then you will see the length being the projectile motion up and down to the other person. And also, if we take someone that is observing from this view of throw, they will see just going up and down. Right? Now imagine if someone was moving in those different reference frames, then we will see the event of different distances. And that's what we call with length contraction. Because there is a difference in motion between the reference frames, we'll see length or distance happening at a different length or distances, right? So therefore, what we'll do again is to use our Lorentz factor to incorporate in terms of length. So if we calculate length, right, then the length L is the length of the non-moving reference frame, which is also called the proper length, right? So proper length is measuring the length of something when you're stationary, you're not moving in reference to the object. And then L prime is a length measured from a moving reference frame. And then V we know is the speed of the moving reference frame, and C is the speed of light. Now, this is important in basic measurement, right? So when we're measuring something, we are always told that we need to be aligned with what we're measuring. Now, let's take, for example, we're measuring the length of this pen, right? Now, if this pen is moving, but we are stationary, then it's impossible for us to get the accurate length of this pen. If it's moving, we have to move at the same speed. So in relative to each other, we are not moving, right? But once there is relative motion to what is being measured and the observer measuring the object, then there will be some length difference. And that length difference is what we call length contraction. Now, that is the end of today's lesson. All right, these are just examples to show how we utilize that equation. All right, so that's it for us this week, guys. We'll see you next week as we explore the final aspect of relativity, which would be the space-time diagrams. So stay tuned next week as we explore more on our IB physics syllabus on the topic of relativity.